Write a short statement that expresses a possible relationship between the variables, a size of a diamond, and the cost of a diamond, okay? So the first question I have for you, okay, is which one comes first? Do you pick a price or do you pick a size? Which one comes first? Well, the truth is, what's causing the other one? The size of the diamond is not something you change based on cost. The size of the diamond is our independent variable. The cost of the diamond depends on how big it is. That's one of the things it depends on. So what we can say, if we were to just kind of generally say it, as the cost goes up, the size also goes up. Now, if we put that, that is not the best possible answer, okay? The cost goes up, the size goes up, because we put it in the wrong order. The independent variable should come first. So the better answer is to say that as the size goes up, then the cost goes up. Now, to be fair, there's actually a flip way we could do this, right? We could do one more version. We say as the size goes down, then the cost would go down. They're in the same direction. So even if we said down, it still is a mathematical relationship. Identify the independent and dependent variables and describe the domain and range. Okay, so first off, the independent variables are always our x value. It's also going to be where we look for domain, which means we have our dependent variables are our y values. Which means it's going to be where we look for our range. So let's look at how we'd actually say what our domain or range would be. So our domain would be, let's see, what possible value do we have for the domain? Well, we have the numbers 1950 and up until the year 2000. And I use square brackets, I use that notation, but I'm really just saying all the years between 1950 or 2000, that's what we're talking about here. The range, what we're going to do is we look on the left side and we say, where's the bottom and top of this? Okay, and it looks like it's about 2.2 billion, and it goes to about 6 billion. Consider this data. So we have this graph, and this is bar charts. Now, it's bars, unlike a line chart. It means we just have each of these are representing separate categories. And in this case, our categories are different countries. We also have, these are a side-by-side bar chart, so we have two groups in each country. In this case, boys and girls. Okay, so let's look at the kind of questions they ask us when we look at this that we want to be able to analyze. The first thing we want to look at is if we were to notice, it says that the bar graph from country E is more than twice as long as the bar graph from country D. So let's look at what that they're saying there. They're saying country E, for the girls, is more than twice as high as the bar for D. Does that mean they scored twice as high? So does that mean they scored twice as high? Well, let's take a look at what the scores represent. If we would continue this bar and look over here, is 540 twice as high as, I don't know, 490? No, it's not. So why is it not true that E is scores twice as highly as D? Why does it look like it is when it's not true? And that's because the axis, okay? So it doesn't start at 0. Y axis doesn't start at 0. Okay, so that's a big problem with the way we look at this graph. If we were to zoom out and put this starting at 0, these numbers are actually pretty close together. It's not nearly as spaced out as it might look when we're zoomed in right here. Part B says, assume that the data in the figure represents overall regional differences in performance. Okay, so the ups and downs are supposed to say, yeah, are we showing something consistent? So, and it says, imagine that country G is right next to country F. So we have F and G is in the same region as, suppose country G is in the same region as B and F. So it's actually in B and F. So I'm looking at B and F. B and F. And I want to see what would I expect for the boys and girls to score in G if they have the same results as we saw in B and F. Well, what happened in B and F? Well, the boys and girls both scored pretty well, and the girls scored better. So I would expect in G that the girls would score a little better. When we're looking at data in a table and we need to convert it to data in a graph, we need to be able to choose the data table and graph match that makes the most sense. Okay, and so let me give you an example here. This example, we have years as our dependent variables, so that's along the bottom, and you'll see that that's actually true, right? It's along the bottom of both of these. Both of them are years. Okay, and then we also have a median age, and both of them say median age. So I want you to notice first off that the data is right. You don't need to go zooming in here. Obviously, we can see that out of these two, the data is right. And so that's the first thing you need. If you're going to have a good graph, it's got to be the right data. Okay, obviously. The other thing we got to watch out for is, did we pick the best graphical display for our data? And if we have years on the bottom, if we have years, or if we have time, we're going to usually use that right there. So if time is our independent and we're showing a change over time, we generally don't use bar graphs. Okay, so the question would then be, well, when do we use bar graphs? Because I feel like a lot of times we use time as our thing. Well, we use that when we have categorical data. In other words, is our independent variable, or is our X a category? And in this case, it's not really a category, it's a time. So it's showing, it's a number, it's quantitative. But if I had to split it up into, say, different groups from different countries or from different teams, then those are different categories, not the same group across time. Using this frequency table on the left, I want to look at which histogram is the best fit for this. Now, histograms are kind of like bar charts, except they represent data that is quantitative on the bottom. In other words, they're numbers, and they're numbers that have kind of like breaking points. So each one of these represents a bucket that we're going to fill up. Now, this one hopefully isn't too scary to you because we have the number 0 for our smallest group, from 20 to 29, 0 actors. And that one has 0 actors, but I want you to notice this one does not have 0 in the first group. Okay. The next thing we're going to do is we're going to look at the end. Now, the smallest, it seems to get bigger in the middle and then it tails off. So if I were kind of like sketch a graph of what this would look like, I'd say 0 and then 10 and then 14 and then 6 would be less than that, and 3 would be less than that, and 2 would be like that. So I just really quick was able to sketch representative of what this should look like. And so I think there's one that looks just like this. Okay, I think it's this one. You notice that the other ones kind of change directions on us, and so they throw us off a couple times. Compare A and B in 3 ways, where A is 1.6. So we're writing ratios here, and it just tells us what to do, except when we're writing ratios, we generally write them as percents or fractions. There is that ratio where we have a colon, the 2 dots, like it looks like it's a time, right? But we're going to go ahead and write these ratios as fractions in this course. So when we say ratio of A to B, what we're saying is put A over B, okay? And so all that needs us to do is type in 1.6, and I can not even type the million. I don't need it because they both have million, and 2.3. If I were to type million on the top and bottom, it would cancel out anyway. And then that would be my answer for part A. For B, however, I need to flip it upside down because it says ratio B to A, so B has to go on top. 2.3 over 1.6. And the last part says A is what percent of B, okay? So A is what percent of B means we take that ratio from part A and we turn it into a percent. Now, how do you convert this fraction, this ratio, to a percent? Well, all we have to do is type it into our calculator, get the decimal, and then multiply by 100, or move the decimal place too. First up, in the following situation, we want to state whether two variables are related in any way, and in a way that might be described as a function, and if so, which one is the independent and which one is the dependent variables. Okay, so independent variable and dependent variables. Reminder that independent variable is our x usually, and dependent variables are y if we're using x and y as our stuff. So let's look at a situation here. You have an expensive phone bill and you want to know how the cost of the bill depends. Okay, well, they kind of gave it to us here. They said depends. Okay, so that means we're going to definitely have an x and y relationship. There's a dependent. So it says the cost of the bill, that's one part, depends on the time you spent. Okay, so which one is causing which? So which one depends on which, okay? So the dependent variable is the one that depends. So we say the cost depends on the time we spent. So in that way, it's actually telling us the dependent variable is what depends, okay? What does it depend on? It depends on the independent variable. So this would be a function, and it would depend on the amount of time you spend on the phone. So time on the phone is our independent, and the cost is our dependent. If you have any questions, put them in the comments. Let me know.